Section: Introduction. In this section, we discuss how language models have shown an impressive ability to learn from unstructured text, allowing them to tackle complex knowledge-based tasks. This success stems from the combination of predicting the next word and using vast amounts of internet data. However, we recognize that this method is not very efficient in terms of data usage. For instance, a 13-year-old human learns from less than 100 million words, while top open-source models are trained on 15 trillion words. We also note issues like the reversal curse, where models find it hard to learn relationships when the training data is presented in a reversed manner, and the need for models to see thousands of examples for each fact to learn effectively. These challenges make it difficult to adapt the next word prediction method for smaller datasets. Since large pre-trained models already hold much common knowledge, future improvements will require learning from less common data, which is often found in small, private collections or appears infrequently online. To tackle the problem of learning from small datasets, we propose using synthetic continued pre-training. For example, if we want to teach a model about a specific area of mathematics documented in a few textbooks, directly training on those texts may not work well due to their limited size. In contrast, established fields like linear algebra are easier to learn from because there is a wealth of diverse resources available, such as online notes and discussions. Synthetic continued pre-training helps by transforming a small, limited dataset into a larger, more varied synthetic dataset, which we can then use for further training. One simple method is to paraphrase the original texts in different ways. However, we find that this approach alone does not create enough diversity in knowledge representation. After several rounds of rephrasing, the model's performance plateaus because it lacks new information. To overcome this limitation, we introduce EntiGraph, an algorithm that focuses on entities within the text. It breaks down the text into a list of entities and uses a language model to generate descriptions of the relationships between these entities, effectively building a knowledge graph. To measure our progress in acquiring knowledge from small datasets, we set up an experiment using a standard reading comprehension dataset. This allows us to evaluate our synthetic data generation methods without the high costs of starting from scratch. Specifically, we work with a collection of 265 books totaling 1.3 million tokens and aim to create a synthetic corpus that enables a model to answer questions related to the book content without needing the original texts. In our main experiments, we use EntiGraph to generate 600 million synthetic tokens from the 1.3 million real tokens. We then continue training the Llama 3 model on these synthetic tokens and assess its accuracy in answering questions. We observe a clear trend where accuracy improves as the number of synthetic tokens increases, reaching a point where using 600 million synthetic tokens gives us 80% of the accuracy we would have if we had access to the original documents. Additionally, we find that instruction tuning the continually pre-trained model allows it to handle a wider range of tasks related to the books. Our key contributions include proposing the use of synthetic continued pre-training to expand small datasets into larger, diverse ones, and demonstrating that this method significantly improves question answering accuracy compared to just using original documents or paraphrases. We also explore an open book setup where the model has access to the original texts while answering questions. Our findings show that the knowledge gained through synthetic continued pre-training complements what can be retrieved through other methods. Finally, we develop a mathematical model that explains the effectiveness of synthetic data augmentation with EntiGraph, providing a formula that aligns well with our experimental results. Overall, our approach allows pre-trained language models to adapt to specialized areas by acquiring structured knowledge, paving the way for more efficient data generation methods in future training. Section Summary. In this section, we discuss the limitations of current language models in acquiring knowledge from small corpora and propose a solution through synthetic continued pre-training using our EntiGraph algorithm. Our approach generates diverse synthetic data from limited source texts, significantly improving knowledge acquisition and performance on tasks like question answering, while also demonstrating that this method is more effective than simple paraphrasing or direct training on small datasets. Section: Related work. In this section, we explore related work on synthetic data generation, continual learning, and knowledge editing. We note that there is extensive research on using neural networks to create synthetic data, particularly for semi-supervised learning. Techniques like self-training and co-training have been used to enhance model performance by training on their own predictions or by having two models supervise each other. Before the rise of language models, few methods focused on generating inputs, with one notable exception being membership query synthesis in supervised learning. Currently, many studies utilize co-training and self-training to boost language model performance, especially in tasks involving mathematical reasoning or by generating input-output pairs for instruction tuning based on a curated seed set. Some methods synthesize pre-training data using hierarchical prompting to increase dataset diversity, such as generating children's stories with specific keywords or creating diverse datasets of textbooks and coding exercises based on topics and audiences. However, these datasets and prompts are often not publicly accessible. We also see approaches that prompt language models to rephrase documents for pre-training, which enhances training efficiency. Our focus differs as we aim to teach a pre-trained language model the knowledge from a small corpus. While some methods propose fact-based synthetic generation, they do not show significant improvements in general instruction following tasks beyond simple question answering. Others have pre-trained models on synthetic paraphrases of Wikipedia articles but did not achieve consistent performance gains. We adapt these methods to our small corpus setting as a baseline and find that our graph-based augmentation algorithm performs better, likely due to its emphasis on diversity through entity-based generation. In terms of continual learning, we recognize its roots in connectionist networks, focusing on learning tasks that arrive sequentially. The main challenge is to prevent a neural network from forgetting previously learned tasks. Various strategies have been proposed, such as regularizing updates to maintain important parameters, modifying the architecture, or recalling past experiences. Continued pre-training has been effective in adapting large language models to broad domains like code, medicine, or mathematics by using extensive datasets and efficient training methods. However, we aim to apply this success to smaller, specialized domains, noting that standard continued pre-training is less effective with small corpora. Therefore, we propose a knowledge graph-inspired method to create a diverse related corpus that is more conducive to learning. In the realm of knowledge editing, we find literature that updates language models with small factual knowledge units, like subject relation object tuples. Some studies focus on constrained fine-tuning to help models learn simple factual relationships, while others localize factual knowledge within transformers or maintain an external memory of edits. The most relevant approach to our work is deductive closure training, which deduces implications from factual edits and fine-tunes the model accordingly. However, our goal is to learn from a small corpus of documents rather than from isolated facts. Our method centers on acquiring parametric knowledge from a small text corpus. Specifically, we aim to continually pre-train a language model to learn from a niche set of documents. We observe that straightforward continued pre-training on this corpus is ineffective, so we propose synthetic continued pre-training, which first synthesizes a larger corpus from the small one to facilitate learning, and then continues pre-training on this synthetic dataset. In this section, we will detail our problem setup and evaluation approach, followed by a specific implementation of synthetic continued pre-training using a data augmentation algorithm called EntiGraph. We focus on how continued pre-training can adapt language models to various domains, but it typically requires large, diverse corpora with billions of tokens. Given the success in high-resource domains, we aim to extend these methods to niche areas where only small, specialized text corpora are available. Our focus is on using continued pre-training to impart the knowledge of a small set of source documents to a pre-trained language model. Section Summary. In this section, we review existing methods for synthetic data generation, continual learning, and knowledge editing, highlighting their limitations in adapting language models to small, specialized corpora. We propose a novel approach that synthesizes a larger, diverse dataset from a small corpus to enhance continued pre-training, aiming to effectively teach a language model the knowledge contained within niche documents. Section: Synthetic Continued Pretraining, Synthetic CPT. In this section, we discuss Synthetic Continued Pretraining, Synthetic CPT. We observe that simple continued pretraining does not effectively capture knowledge from a small dataset, which we refer to as Ds, even when we repeat the data. We believe this issue arises because Ds is very compact, containing only about 1.3 million tokens, and lacks variety in how the knowledge is presented. To overcome this challenge, we propose a two-step process for synthetic continued pretraining. First, we use a synthetic data generation algorithm, which we call AlgSynth, to transform the small dataset Ds into a synthetic dataset, DSynth. Then, we perform continued pretraining on DSynth instead of directly on Ds. We implement AlgSynth using language models, but we are cautious about the potential for these models to create inaccurate information. Therefore, we focus on algorithms that ensure the generated data remains true to the original documents. Next, we evaluate the effectiveness of AlgSynth by checking if the downstream model has successfully learned the knowledge from Ds. We create test queries, QT, that assess the model's understanding of Ds. For instance, in a linear algebra context, these queries could be exam questions. To evaluate the model's knowledge, we do not allow it to access the original dataset during testing, ensuring that the queries are clear without that context. We set a success criterion based on retrieval-based methods, which perform well with small datasets. We consider AlgSynth successful if the model's performance on QT is close to that of a retrieval approach that has access to Ds during testing. We then introduce EntiGraph, our version of the synthetic data augmentation algorithm AlgSynth. EntiGraph generates diverse representations of knowledge from the small dataset Ds by using a prompted language model to create a knowledge graph. This process is applied to each document in Ds. For each document, we use a language model to generate a knowledge graph that represents the entities within that document. EntiGraph consists of three main steps. First, we extract important entities from the document. Second, we describe each entity in the context of the document. And third, we analyze the relationships between different entities. This structured approach allows us to create diverse synthetic text based on a graph of related entities. In the first step, we extract a list of key entities from the document by prompting the language model with an entity extraction request. For example, if our document is a linear algebra textbook, we might extract entities like linear space, vector, and SVD. In the second step, we generate additional context for each extracted entity. We iterate over the entities and use a description prompt to create a synthetic document that explains the role of each entity within the original document. For instance, if we are describing linear space, the synthetic document might explain its defining algebraic properties. Overall, in this step, we create a synthetic corpus that includes a document for each extracted entity, forming a comprehensive representation of the knowledge contained in the original dataset. Section Summary. In this section, we propose a two-step synthetic continued pretraining, synthetic CPT, approach to enhance knowledge acquisition from a small, condensed corpus by generating a synthetic corpus through a data augmentation algorithm, EntiGraph. This method involves extracting entities from the original documents and creating diverse representations of knowledge, which we evaluate against knowledge-intensive queries to ensure the model effectively learns the underlying information. Section: Step 3. Relation Analysis. In this section, we analyze the relationships among subsets of entities as the final step of our EntiGraph process. Our goal is to thoroughly examine the connections within the knowledge graph that supports the source document. This is similar to how a student might take varied notes while studying a linear algebra textbook. We use a relation analysis prompt to explain how a group of entities relates to the source document, resulting in a new synthetic document that represents these relationships. Since it is not feasible to list all possible combinations of the extracted entities, we focus on generating all pairs and triplets of entities. We gather all the synthetic texts produced by the EntiGraph algorithm from the source document, creating a collection of synthetic texts. We apply this method to each document in our dataset, resulting in a larger synthetic corpus. Next, we detail how we evaluate our data augmentation algorithm. We assess whether a language model, which has been continually pre-trained on the synthetic corpus, can accurately respond to test queries about the source documents. In our main experiments, we use clear queries that do not require access to the source documents, allowing us to determine which data augmentation method best enhances knowledge acquisition. We utilize the quality dataset for our corpus and test queries. This dataset consists of 265 articles and short books across various genres, averaging around 5,000 tokens in length. For our test queries, we draw from multiple choice questions associated with each article, ensuring they are unambiguous by providing context from the corresponding article. This results in a total of 4,609 clear queries, with a subset labeled as hard for additional analysis. Finally, we also instruction tune our continually pre-trained language models and evaluate their ability to summarize quality articles based solely on their titles and authors. Section Summary. In this section, we analyze the relationships among subsets of entities from the source document using a relation_analysis prompt, generating synthetic documents that describe these relationships. We then evaluate our data augmentation algorithm by testing how well a language model, pre-trained on the synthetic corpus, can answer unambiguous queries about the source documents, utilizing a diverse corpus from the quality dataset. Section: Performance with strong API-based LLMs. In this section, we evaluate the performance of strong API-based large language models, LLMs. For our ongoing pre-training, we need to choose a dataset, referred to as Ds, that isn't already well represented in typical pre-training datasets. To test how obscure the quality dataset is, we assess GPT 3.5 and GPT 4 using a set of test queries, QT. In a closed book scenario, GPT 3.5 achieves an accuracy of about 44.81%, while GPT 4 reaches 51.30%. In an open book scenario, where the entire article is included in the prompt, GPT 3.5 feet's accuracy rises to 72.60% and GPT 4's to 86.09%. The significant improvement of around 30% when using Ds indicates that this corpus is sufficiently niche for our testing purposes. Next, we present our main experimental results. We utilize GPT-4 as our prompted model, LMGen, and apply EntiGraph to the 1.3 million token corpus, Ds, generating a synthetic corpus of 600 million tokens. We will refer to the original dataset as the raw corpus, and the synthetic one as the EntiGraph corpus. We continue pre-training the Llama 3.8b model using standard causal language modeling on the 600 million token EntiGraph corpus. We describe our pre-training process and introduce two natural baselines. We evaluate all methods on the quality test queries, QT, and find that the synthetic captain using EntiGraph significantly outperforms both baselines, with accuracy improving log linearly with the amount of synthetic data, up to 600 million tokens. We also demonstrate that synthetic captain using EntiGraph works well with downstream instruction tuning, which is a key feature of effective pre-training data. For our continued pre-training procedure, we keep training the Llama 3.8b base model with a context length of 2048 and a batch size of 16. We implement a linear learning rate warm-up for 5% of the total steps, followed by a cosine decay, reaching a peak learning rate of 5 millionths. We conduct full parameter training using fully sharded data parallelism, FSDP. To prevent the model from forgetting previously learned information, we incorporate a replay mechanism with a rate of 0.1, using 1 billion red pajama tokens. Specifically, for each training batch, we use a biased coin flip to decide, with a 10% chance, to load red pajama data instead of the EntiGraph synthetic data. In our main pre-training experiment, we continue training the Llama 3.8b base model on the 600 million token EntiGraph corpus for 2 epochs. We will refer to this continually pre-trained model as EntiGraph CPT. We then outline two baselines for comparison with EntiGraph CPT in closed book question answering and instruction-tuned summarization evaluations. The first baseline, called raw CPT, involves continuing the pre-training of the Llama 3.8b base model on the raw corpus, which consists of the original quality articles. Since the raw corpus contains only 1.3 million tokens, we adjust the number of epochs and the red pajama replay rate based on accuracy from a validation split. We select a configuration of 4 epochs and a replay rate of 0.1. The second baseline, known as the rephrase baseline, involves a simple data augmentation technique where we rephrase quality articles using a generic paraphrasing prompt. We extend this idea systematically by rephrasing the original data into 4 different styles: easy, medium, hard, and question answering, using the same prompted model, LM-Gen, as with EntiGraph. We apply these prompts to every document in Ds, resulting in approximately 0.9 million tokens. However, we found that the limited diversity of LM-Gen with these prompts hindered further improvements, so we stopped after a second pass, totaling 1.8 million tokens. We will refer to this dataset as the rephrase corpus and continue pre-training the Llama 3.8b base model on it using the same hyperparameter tuning process as before, calling this model rephrase CPT. Section Summary. In this section, we evaluate the quality corpus's effectiveness for continued pre-training by testing GPT 3.5 and GPT 4, finding significant accuracy improvements in both closed book and open book settings. We then describe our main experiments using the EntiGraph synthetic corpus for continued pre-training of Llama 3.8b, which outperforms natural baselines and demonstrates compatibility with downstream instruction tuning. Section: Question Answering Evaluations. In this section, we outline our closed book question answering evaluations, detailing the setup and results. Each question we use is a multiple choice question with 4 options, similar to the MMLU format. We evaluate using a 4-shot chain of thought prompting method, and we include our prompt in the appendix. For our few-shot examples, we create and verify question-answer pairs manually. To prevent any information leakage from the books, we select well-known books that are not part of the test set. We discover that continued pre-training on the 600 million token EntiGraph corpus boosts the closed book QA accuracy from about 39.49% to 56.42% for the Llama 3.8b base model. We investigate how performance changes as we synthesize and train on more tokens from EntiGraph. To do this, we randomly select different sample sizes from the EntiGraph corpus, continue pre-training the Llama 3.8b base on each sample, and plot the accuracy against sample size. We observe a log linear increase in accuracy as we use more synthetic tokens for pre-training, up to 600 million tokens. We hypothesize that the accuracy follows a 3-stage pattern: initial linear growth, then log linear growth, and finally reaching a plateau. When comparing with baselines, we note that the rephrase captain achieves an accuracy of 43.08%. Applying 4 rephrase prompts to each quality article results in only 0.9 million tokens, and the performance of rephrase captain levels off around this token count. To illustrate this plateau, we generated a total rephrase corpus of 1.8 million tokens and found similar performance to the 0.9 million token model. In contrast, the EntiGraph captain accuracy continues to rise beyond 1.8 million tokens, reaching up to 600 million tokens. The raw captain performs even worse than the Llama 3.8b base model. We suggest 2 reasons for this. First, the raw corpus has a narrower distribution than the Llama 3.8b pre-training corpus, which may negatively impact the model's overall English skills. Second, the limited diversity in the raw corpus restricts knowledge acquisition due to issues like the reversal curse. From our continued pre-training experiments, we highlight 2 key insights. First, when the source document corpus is small, the knowledge is condensed, and continued pre-training with next token prediction does not effectively teach the model this knowledge, even with heavy repetition. Second, Creating a larger synthetic dataset based on the source documents can help a continually pre-trained model learn this knowledge. However, for synthetic data to be effective, it must be diverse enough. EntiGraph addresses this by using a hierarchical prompting strategy that enhances diversity through the relationships in entity knowledge graphs. Next, we explore broader test queries beyond the quality test queries. Specifically, we train EntiGraph Instruct by tuning it on the EntiGraph captain. We show that synthetic captain on the EntiGraph corpus works well with instruction tuning. Notably, EntiGraph Instruct can utilize knowledge gained during synthetic captain for instruction following tasks without needing access to the source documents during testing. For instruction tuning, we use the UltraChat dataset filtered by the Hugging Face team. We format the conversations using the chat template of Llama 3.18b Instruct, resulting in a 250 million token instruction tuning dataset. We apply a learning rate warm-up followed by a cosine decay, with a peak learning rate of 5 millions, and train the model for one epoch with a batch size of 512 and a context window of 2048. To verify our instruction tuning process, we check the Alpaca eval win rate against GPT-4, which improves from 0% to 6.35%, compared to a baseline win rate of 7.7% for Llama 2 Chat 13b. We also present qualitative examples to showcase EntiGraph Instruct's ability to follow instructions related to quality articles. In our first test, we ask the model to summarize a quality article using only the title and author as references, without access to the article itself. Next, we demonstrate that even without explicit references, the model retains knowledge of the article and its parameters, influencing its responses. Finally, we provide an example where the model compares knowledge from two articles, showing that even though EntiGraph does not synthesize data involving multiple articles simultaneously, the model can reason about their interactions based on its learned knowledge. We include the full responses in our tables. Section Summary. In this section, we detail our closed-book question-answering evaluations, demonstrating that continued pre-training on the 600M token EntiGraph corpus significantly improves accuracy and exhibits log linear scaling with sample size. We also explore instruction tuning with the EntiGraph corpus, showing that our model can effectively follow instructions and utilize knowledge from synthetic data without direct access to source documents. Section: Evaluation metric for closed book summarization. In this section, we present evaluation metrics for closed book summarization, focusing on a well-known task of following instructions. We compare the summaries generated by EntiGraph Instruct for quality articles with human-written summaries from a variation of the quality benchmark called SQ-ality. Traditional metrics like Rouge and BERT score mainly assess how similar the summary is to the original text, which may not accurately reflect the performance of abstractive summarization systems. To address this, we propose a straightforward automated evaluation method inspired by pyramid evaluation. This method assesses both the rate of inaccuracies and how well the summary captures the key points of the original article. Our evaluation process consists of 3 stages. 1. We first use GPT-4 to break down the summary into individual claims. 2. Next, we provide these claims along with the original article to another model, also GPT-4, which determines if each claim is true or false. If a claim is true, we further classify it as either salient, important for understanding the article, or cosmetic, not essential. 3. Finally, we count the number of false and salient claims in each summary and normalize these numbers against the human summary counts. We then report the average of these normalized metrics across the articles. In our discussion of the quantitative results, we compare 3 summarizers: EntiGraph Instruct, Rephrase Instruct, and Raw Instruct. We give each summarizer 3 different prompts, short, medium, and long, to elicit summaries of varying detail. We find that Rephrase Instruct and Raw Instruct tend to generate more inaccuracies as the summaries get longer, with minimal improvement in salient claims. In contrast, EntiGraph Instruct produces more salient claims with only a slight increase in false claims, indicating that these results are likely consistent beyond our specific metrics. We also include qualitative examples in the appendix, comparing short summaries from all three summarizers against human summaries. We observe that EntiGraph instruct's content aligns well with human summaries, while raw and rephrase instruct show noticeable inaccuracies, confirming our automated evaluation findings. Next, we explore an open book scenario where the domain-specific corpus is available during testing. In this common setting, retrieval augmented generation, RAG, is the preferred approach due to its effective tools, avoidance of fine-tuning, support for ongoing learning, and high recall rates. We investigate whether the knowledge gained through synthetic captain using EntiGraph enhances the non-parametric knowledge accessed during testing with RAG. Our RAG pipeline adheres to established best practices, involving an offline stage for indexing document chunks, followed by retrieval, re-ranking, and integration of these chunks into a few-shot language model prompt. Specifically, we chunk documents from the corpus, create dense vector embeddings for each chunk using an API-based model, and index these pairs. During inference, we embed the query, retrieve document chunks using approximate nearest neighbor search, and select the most relevant chunks with a re-ranker. We utilize OpenAI's text embedding 3 large for embeddings, FAISS for similarity search, and Cohere's re-rank English v3.0 for re-ranking. Finally, we evaluate parallel RAG pipelines on a multiple-choice test set using few-shot chain-of-thought prompting, tuning hyperparameters for each language model's RAG pipeline. More details on our evaluation setup can be found in the appendix. Section Summary. In this section, we present a novel evaluation metric for closed-book summarization that assesses both the hallucination rate and the salience of claims in summaries generated by our model, EntiGraph Instruct, compared to human written summaries. We also explore the effectiveness of retrieval augmented generation, RAG, in an open book setting, demonstrating how our approach can enhance the retrieval process and improve summarization outcomes. Section Results. In this section, we present our findings in the open book RAG setting, as shown in the table. We found that continuing the pre-training of EntiGraph enhances RAG performance. Notably, EntiGraph's continued pre-training outperforms the Llama 3.8b base model from which it was derived. This indicates that the knowledge gained through synthetic continued pre-training adds value to what is accessed during RAG, leading to an effective approach for small corpus question answering. Our method includes 3 key steps: using synthetic data augmentation, continued pre-training, and RAG. We also observed that EntiGraph's continued pre-training alone nearly matches RAG's performance. When we compare the results, we see that adding RAG to Llama 3.8b base improves accuracy by about 20.86%, increasing from 39.49% to 60.35%. In contrast, continued pre-training of Llama 3.8b base on the EntiGraph corpus results in a 16.93% accuracy boost, from 39.49% to 56.42%. This shows that EntiGraph's continued pre-training accounts for over 80% of the accuracy improvement seen with RAG, even in a small corpus context where RAG's recall is almost perfect. Overall, our results highlight that the knowledge gained from EntiGraph's continued pre-training integrates well with knowledge-intensive question-answering systems, and that this pre-training alone, without accessing the corpus during inference, comes close to matching a strong RAG baseline.